Gases. Gases have an indefinite volume and an indefinite shape. So they expand to fill a container and take the shape of the container. And they have high kinetic energies. The kinetic molecular theory. There are some assumptions made. Gases consist of tiny particles. The distance between the particles is large compared with the size of the particles. Gas particles have no attraction for each other. Gas particles move in straight lines in all directions, colliding frequently with each other and with the walls of the container. So it's kind of like that old screensaver if you ever had a computer up where you see the item in the center and it bounces from one part of the screen to the next, to the next, to the next. That is kind of like how gases work. So each gas particle, each molecule within the gas is going to go in a straight line, colliding with the edges of the container or colliding with each other. Diffusion of gases is the movement of gas particles from an area of high concentration to an area of low concentration. Gas particles will diffuse until there is an equal balance of equal concentration of gas on both sides. So you can see in this diagram, you have a lot of concentration over here and no concentration here. If you were to open up the valve, gas particles will flow from the area of high concentration to low concentration until the particles are equally spaced apart. Pressure. So pressure is equal to force over area. Pressure depends on the number of gas molecules, the temperature of the gas, and the volume that the gas occupies. Atmospheric pressure is due to the mass of the atmospheric gases pressing down on the Earth's surface. A barometer is used to measure pressure. So 1 atm is equivalent to 760 torr, 760 millimeters mercury, 76 centimeters mercury, 101.325 kPa, 1013 mbar, 29.9 inches mercury, and 14.7 pounds per inch squared. You should make a note of these because these are conversion factors that we'll use when converting between units of pressure. So convert 675 millimeters mercury to atm. So if we do this problem, we have 675 millimeters mercury, and we want to convert to atm. So 1 atm is equal to 760 millimeters mercury. Let me grab my calculator here. So when we divide these, we do 675 divided by 760, and we get 0.888 atm. So now it wants to convert 675 millimeters mercury to torr. So 760 millimeters mercury is equal to 760 torr. In other words, they're identical. So 675 millimeters mercury is going to equal to 675 torr. A pressure of 3 atm is equal to, you can pause the video, do the conversion. All right, so 2280 torr. The dependence of pressure on number of molecules. So P is proportional to N. Pressure is proportional to n, the number of molecules. The more molecules you have, the higher pressure. Think about trying to pack a whole bunch of people into a crowded gym. So the closer or the more people you are, the closer those people are going to be to each other. And the more pressure they're going to have because they're going to be compacted together, as opposed to only having like 3 people in a huge open gym. They're not going to be very pressured. They're going to have a lot of space to walk around and move around, and it's going to feel open. So P, the pressure, is proportional to N, the number of molecules, at a constant temperature and a constant volume. If we start changing the temperature or we start changing the volume, that can change the pressure. So the increased pressure is due to more frequent collisions with the walls of the container, as well as increased force of each collision. The dependence of pressure on temperature. Pressure is proportional to temperature if we have a constant number of molecules and a constant volume. The increased pressure is due to more frequent collisions or higher energy collisions. So let me give you a practical example of this one. If you've ever taken a balloon outside in the wintertime, so let's say you are having a birthday party in the wintertime, you order a balloon, you fill it up with helium, and inside of the store it's pretty round and it's, has a constant shape to it. And then as soon as you take it outside, it deflates a little bit. It's not because the molecules are moving to the outside of the balloon. There's still the same number of particles inside. It's because the temperature has changed. When the temperature changes, things condense. When things get colder, things are going to condense. So those molecules are going to condense together a little bit. Also, when you have a decrease in temperature, the molecules are going to move less frequently. So that decrease in temperature is going to cause a decrease in the collision, which is going to decrease the pressure within that balloon. Now, if you take that same balloon and you bring it back inside, it's going to reinflate. The temperature inside is going to be warmer than the outside temperature, and you're going to have those molecules spread out again, and you're going to increase the collisions between those molecules because you're increasing the temperature. Think about the pressure, again, back to that crowded gym. If you have a very hot temperature inside of that crowded gym, you are going to have a lot more pressure. It's going to be really uncomfortable. If it's really cold, the people inside of the gym are going to want to cluster together for warmth. So they're going to condense down into the center, and you're not going to have a lot of pressure. You're going to decrease the pressure because they're not going to be bouncing off the walls of the outside of the gym. They're all going to be clustered together for warmth. So temperature and pressure are related. So if you change the temperature of a sample of gas from 80 degrees Celsius down to 25 degrees Celsius at constant volume, the pressure of the gas is going to do what? Pressure decreases. So when you have a decrease in temperature, you're going to have a decrease in pressure. Boyle's law. Boyle's law relates pressure and volume. And Boyle's law has a lot to do with how we maintain our blood pressure, how we maintain breathing. So I will relate this to how we breathe and how air comes into our lungs. So what Boyle's law states is that volume and pressure are inversely related. So as volume increases, pressure decreases. As volume increases or decreases, pressure increases. So they are inversely related. So Boyle's law states P1V1 equals P2V2. If you double P, V decreases by half. If you double V, P decreases by half. So let's think about this. We have our lungs, and inside of our body, in order to breathe in, we actually increase the volume of our chest cavity. So we use our muscles, our external intercostals, and our diaphragm, and those are both going to contract, and that causes the volume of our chest cavity to increase. So when we increase the volume of our chest cavity, the pressure inside of our lungs decreases. So that allows air to passively flow from the atmosphere into our lungs down its pressure gradient. Now to breathe out, we relax those muscles. So we're going to relax the muscles, our chest cavity is going to collapse, and air is going to come out. The reason why air comes out is because we're increasing the pressure inside of our chest cavity. Think about a water hose. If you're holding a water hose with no nozzle on the end, the water is going to pour out. If you put your thumb over the end of that water hose, water spurts out at a very fast rate. The reason is because when we decrease the volume that the water has to go through, we increase the pressure. So those molecules are going to become more condensed, and then they're going to spurt out farther because we're going to increase the collisions of the molecules with each other. So putting your thumb over the end of a water hose, that increases that pressure. If we have an unhealthy lifestyle and we end up accumulating a lot of fat inside of our arteries, that fat is going to cause a constriction. It's going to coat the inside of our blood vessels, which constricts the blood flow. That's going to increase our blood pressure. So Boyle's law, not only related to breathing, it's related to blood pressure, it's related to a lot of the things in the human body. It's one of the most important laws to know when we're talking about general chemistry if you're going into the healthcare field. So now we can do some calculations. A sample of argon gas occupies 500 mils at 920 torr. Calculate the pressure of the gas if the volume is increased to 937 mils at constant temperature. To solve this problem, you're going to have to figure out what the variables are. Now the units don't matter as long as they match. So whatever units are in the problem that you're going to plug into this equation, they have to match. So far our volume units are mils and mils, which is good. We can plug those directly into the equation. If they were mils and liters, we would have to convert one to the other unit so that they would match before plugging them in. Our pressure unit is torr. So we're starting out with a volume 1 and a pressure 1, and we are converting to a volume 2, which we don't know, or sorry, pressure 2, P2, and here's our volume 2. So now we can just plug this into the equation. P1V1 equals P2V2. So we have 920 times 500, and we're going to set that equal to P2 times 937. And we can treat this like just any old variable. We can treat that like x. So instead of writing it this way, we could do 920 times 500 equals 937x. So now we're going to do 920 times 500, and then we're going to divide the 937 away from the x. And we end up with 490.9. So we have 3 sig figs that are in the problem. We're going to round this to 3 sig figs. So we get 491, and our unit, our pressure unit, is torr. So a 6-liter sample of a gas at a pressure of 8 atm is compressed to 4 liters at a constant temperature. What is the pressure of the gas? Go ahead and pause the video and then we will resume. Okay, so again we have our P1V1 equals P2V2. And we have to identify the variables here. We see liters, we know that's a volume unit, and we have a 6-liter sample of gas at this pressure. Pressure unit is atm. So this is our V1, and this is our P1. And we're wanting to find out what would happen to the pressure if we compressed it to a smaller volume. So we have our V2, and we need to know our P2. And now it's saying at a constant temperature. That may or may not be written in the problem. It's just saying that the temperature is not changing. Because if the temperature did change, then we'd have to take that into consideration as well. But it's not changing, so we can just use this equation as is. So P1 is 8. V1 is 6 equals, we don't know what P2 is, but we know that V2 is 4. So now we're going to do 8 times 6, divide away the 4, and we get 12 atm. A 400 ml sample of gas is at a pressure of 760 torr. If the temperature remains constant, what will be its volume at 190 torr? So go ahead and pause, and then we will work on this one together. Okay, so we have P1V1 equals P2V2. We're going to identify the variables here. So we have pressure, and a volume. So we have volume 1, pressure 2, and we are trying to figure out volume 2. So pressure 1 is 760, volume 1 is 400. We're going to set that equal to our pressure 2, 190, and our volume 2 we don't know, so we're just going to use the letter X. So 760 times 400 equals, and then divide away the 190, and that's what we get.